Imagine a solid steel shaft, right? And it's spinning at like 60,000 revolutions per minute.
Yeah, which is 1,000 rotations every single second.
Right, 1,000 times a second. I mean, at that blistering speed, just a single microscopic speck of dust in the wrong place can throw the entire assembly completely out of balance.
Oh, absolutely.
Oh.
Or even just a seemingly harmless, 3-degree rise in internal temperature.
Yeah.
That alone can cause the metal to physically grow just enough to instantly turn a $100,000 aerospace component into, well, useless scrap.
It's crazy.
It is an incredibly hostile, unforgiving physical environment, and yet this is the environment where the vast majority of our modern world is actually built.
Yeah.
We're talking about the hidden spinning heart of precision manufacturing, which is the CNC milling machine spindle.
And that is exactly the focus of our deep dive today. We've pulled together technical manuals, engineering breakdowns, industry analyses to really decode a highly consequential choice in manufacturing for you.
Right, because making the wrong choice here is expensive.
Massively expensive. We are looking at the fundamental structural differences between two specific types of spindles. You've got the electric or motorized spindle and then the direct drive spindle.
Which, to anyone just looking at them, they seem pretty similar.
Right, but our mission today is to understand why confusing these two systems or, deploying the wrong one on a factory floor inevitably leads to just catastrophic production failures and massive financial losses.
The stakes really are incredibly high because, like you said, from a distance, they sound like they do the exact same job, right? I mean, they both run on electricity.
Right.
They both spin a cutting tool. They both remove metal. But beneath the housing, their internal structures are engineered to solve vastly different physical problems.
Exactly. I mean, buying a spindle based on just one metric, like speed, it's kind of like buying a high-end sports car for a tractor pull.
That is a perfect way to put it, yeah.
It might have a ton of horsepower, but it's going to get destroyed the second you hook a plow to it.
Exactly. The motorized spindles, they favor extreme speed, fast response, whereas direct drive units are all about balancing torque, rigidity, and, frankly, cost and serviceability.
Right. So to really understand what these machines can actually do, we first have to look under the hood at how they are structurally built, right?
Yeah.
And how they deliver power.
Yeah, let's look at the anatomy.
So the literature constantly refers to the motorized spindle as having this zero transmission structure. Okay, let's unpack this. What does that actually mean for the machine mechanically?
Well, think about a traditional drivetrain in a car.
Mm-hmm.
You have a motor, right?
Yeah.
And that motor passes its rotational energy through a belt or maybe a set of gears or a coupling.
Right, a bunch of middlemen.
Exactly, to eventually turn the wheels. Zero transmission means we just eliminate all of those middlemen.
Wow, all of them.
Yeah, in a motorized spindle, the motor's rotor, which is the magnetic core that actually spins, is physically forged or pressed directly onto the spindle shaft itself.
Oh, wow. So there's no connection piece at all.
None. The motor and the tool holder are just one single, cohesive, rotating assembly.
Okay, so by stripping away all the belts and couplings, you are drastically reducing the rotational inertia of the whole system.
Yes.
There's just like way less dead weight to get moving.
Exactly. And that reduction in inertia is the absolute key to their defining characteristic, which is extreme acceleration and staggering top speeds.
Which we mentioned earlier, right?
Yeah. I mean, a standard motorized spindle operates comfortably in the, say, 15,000 to 40,000 RPM range.
Which is already wild.
Right. But for highly specialized applications, like micromachining or fine mold engraving, they can easily exceed 60,000 RPM.
That is just mind-blowing. But then meanwhile, the direct drive spindle takes this completely different mechanical approach.
Totally different, yeah.
It uses a separate, standalone external motor, right, that sits like above or behind the spindle housing, and the rotational power is transferred through an actual physical mechanical coupling.
Right, so you're bringing the middleman back in.
Yeah. And because of this multi-part assembly, the speeds are significantly lower, right? Usually sitting somewhere between 8,000 and 18,000 RPM, maybe hitting 24,000 sometimes.
Right, because the physical presence of that coupling limits the velocity.
How so?
Well, you have to account for the balance of the external motor, the alignment of the two shafts meeting at the coupling, and just the sheer mass of all those components.
Right.
Centrifugal forces at higher speeds would just tear an imperfectly aligned coupled system apart.
Okay, but this brings up a huge question for me. If throughput is the lifeblood of manufacturing,
Which it is.
right, Why would a facility willingly purchase an 18,000 RPM spindle when a 60,000 RPM option exists? I mean, intuition suggests that spinning the cutting tool faster means you cut metal faster,
I did think so, yeah.
which means you produce more parts per hour. So why wouldn't you just always buy the fastest one?
Well, what's fascinating here is the limitation actually comes down to the physics of electric motors. Specifically, the relationship between speed and torque. So speed is how fast the tool spins, right? Torque is the actual rotational force, like the raw muscle driving the tool through the metal.
Right, the pushing power.
Exactly. Now, as an electric motor spins faster, it acts somewhat like a generator, creating a phenomenon called back electromotive force, or back EMF.
Wait, meaning the motor is actually generating a voltage that pushes back against the electrical current trying to drive it.
Exactly. It's fighting itself.
That's wild.
At lower speeds, the motor easily overpowers this. But as the motorized spindle accelerates into its highest speed ranges, that back EMF builds up until it nearly matches the supply voltage.
So it just taps out?
Yeah, the motor literally cannot draw more current. Its power delivery plateaus entirely, and its torque drops off a cliff.
So a motorized spindle spinning at its maximum velocity actually has very little muscle behind it.
Very little.
It's moving incredibly fast, but it's basically weak.
That is the big trade-off.
Yeah.
Direct drive units, however, bypass this limitation entirely by using much larger, heavier external motors that are specifically wound to maximize low-speed torque.
Okay.
They also utilize massive spindle assemblies to handle all that rotational force.
Right, because the sources highlight that direct drive units utilize these specific tool interfaces, things like BT40, CT40, or BBT40.
Right. Those are industry standards.
Yeah, and to clarify for you listening, these aren't just arbitrary part numbers. These are the physical connections where the cutting tool actually locks into the machine.
And they are massive, right? They're these steep tapered cones made of hardened steel.
Yeah.
The spindle uses an internal drawbar mechanism to literally pull that cone up into the housing with thousands of pounds of clamping force.
Wow. Thousands of pounds.
Yeah, it creates an incredibly rigid, unified block of metal.
Which is absolutely necessary when you introduce radial load, right?
Oh, definitely.
Like if you were taking a giant face mill and aggressively hogging out huge chunks of titanium, you are pushing massive sideways force, that radial load, against the cutting tool.
Yep, and if you tried that with a high-speed motorized spindle, it wouldn't just give you a bad cut.
Yeah.
The lack of torque, combined with the immense physical resistance of the titanium, would likely stall the motor entirely, or honestly, just shear the tool right off.
So you would just destroy the spindle.
You would destroy it, yeah.
Yeah.
Direct drive units provide stable, continuous torque at low and medium speeds, specifically to survive those aggressive, heavy roughing operations.
Okay, so you really have to evaluate continuous torque and bearing capacity rather than just looking at the top RPM listed on some marketing brochure.
Exactly. Top speed is only one piece of the puzzle.
Right. But, having the torque to carve out a massive block of steel is crucial, but removing material is only half the battle.
Right.
Which leads us directly into how the physical structure of these machines dictates the final precision of the part. Because raw power is kind of useless if the final surface finish looks like it was chewed by a rat.
Yeah, nobody wants that.
Yeah.
And high rotational speed does not automatically equal a smooth finish. You can be running a tool at 40,000 RPM. But if the machine has microscopic runout, meaning the center line of the tool is wobbling even a tiny bit, or if the system is vibrating, your surface finish is totally ruined.
But the motorized spindle excels at high-speed finishing, right? Specifically because it eliminated that mechanical coupling we talked about.
Exactly. Every transmission component you add to a mechanical system introduces the potential for alignment error or backlash or, elastic deflection.
Right, more parts, more problems.
Yeah.
Yeah.
Even a really high-end coupling isn't mathematically perfect.
Yeah.
By eliminating it entirely, the zero-transmission motorized spindle removes all those variables.
Wow.
The rotor, the shaft, and the tool holder are dynamically balanced as one single rotating mass.
So it basically eliminates the mechanical chatter.
Completely.
To visualize the difference in precision here, I sort of think of the motorized spindle like a flawless figure skater, right? Just spinning seamlessly on the ice. Perfect balance, zero wobble.
That's a great analogy.
But the direct drive spindle is more like a heavy-duty freight train. Immensely stable on its tracks when it's carrying a massive load, but maybe not quite as elegant.
Right, exactly. The direct drive spindle performs better in medium load roughing, semi-finishing, and cutting hard mold steels because it's like that freight train.
Yeah.
It utilizes larger, more rigid spindle assemblies that resist deflection and vibration when the cutter hits physical resistance. A smaller, motorized spindle might literally bend under that same sideways pressure, introducing heavy vibration.
But then the motorized spindle regains its advantage when you move into multi-axis milling, right? Like 5-axis operation.
Oh, absolutely.
Because the sources point out that low rotational inertia isn't just about getting to top speed quickly, it's about agility.
Yeah, agility is key.
Mm-hmm.
Because when a machine is carving a highly complex 3D contour, say, the curved blades of a jet engine impeller, the angle of the cutting tool is constantly shifting.
Right.
And as the tool tilts, the effective diameter of the cutter making contact with the metal actually changes.
Oh, I see.
So to maintain a perfectly consistent cutting speed at the actual point of contact, the machine has to instantly, constantly adjust its RPM.
Wow, so the spindle has to brake and accelerate like hundreds of times a minute.
Exactly. And a direct drive spindle, dragging all that heavy mass of an external motor and a coupling, simply cannot react fast enough.
Right, the train can't turn on a dime.
Right. But the motorized spindle's low inertia allows for that rapid dynamic response, keeping the cutting speed perfectly smooth across those complex geometries.
Okay, we should address a major caveat in the literature regarding precision, though.
Definitely.
Because manufacturers of these spindles routinely market their products as having submicron rotational accuracy. I mean, they claim the runout is less than a single micrometer.
Yeah, and I strongly caution anyone evaluating these machines against taking those marketing claims at face value.
Really? Why is that?
Well, submicron accuracy is a real measurement, sure. But it is almost universally gathered under highly controlled static test conditions.
I see where this is going.
Yeah, the manufacturer spins the bare spindle in a sterile, climate-controlled testing lab without a cutting tool installed, and certainly without pushing it through an actual block of heavy metal.
So it's not real world at all.
Not at all. The reality of a factory floor is a fundamentally different environment.
Right, because a spindle doesn't operate in a vacuum. Finished part accuracy is like this whole complex ecosystem.
Exactly. The spindle is only as accurate as the machine it's bolted to.
Right.
If the heavy cast iron guideways of the CNC machine are worn, or the fixtures holding the metal are even slightly loose, submicron accuracy is totally meaningless.
Wow.
Furthermore, precision requires absolute cleanliness. A single human hair or a tiny piece of microscopic dust trapped inside the tool taper when the machine does a tool change will push the cutter off-center.
Just a hair.
Just a hair.
Mm.
And that instantly introduces runout, completely negating all the hyper-precision the spindle was engineered to deliver. And coupling quality in direct drives is highly important too, because a damaged coupling introduces severe vibration.
Okay, and when you have an imperfectly seated tool or a massive machine taking heavy cuts, you generate friction. Lots of it.
Lots and lots of friction.
And add in the electromagnetic energy pulsing through these high-speed motors, and you run into the ultimate quiet destroyer of manufacturing accuracy, which is thermodynamics, heat.
Yes. Heat is the absolute enemy of precision. It degrades bearing lubrication, introduces dimensional drift, and fundamentally alters the physical geometry of the machine tool while it's cutting.
Right. And in a motorized spindle, this heat problem is really compounded by the design itself.
Oh, heavily. Because you have a zero transmission structure, meaning the bearings, the electrical resistance of the motor, the magnetic losses, they're all crammed into one compact, totally enclosed metal cylinder.
So the energy just has nowhere to go.
Nowhere. The stator, which is the stationary outer ring of copper coils that pulses high-voltage electricity to create the magnetic fields driving the rotor, it generates immense resistive heat. And because everything is packed so tightly together, that thermal energy radiates directly into the bearings and the spindle shaft.
Wow.
This is why motorized spindles cannot just be air-cooled. They require really complex, active liquid cooling systems.
Right. The manuals specify circulating water, oil, or like water glycol mixtures flowing through these tiny cooling jackets machined directly into the housing.
Yeah, and the temperature control of that fluid must be exact.
Like how exact?
I mean, perfect. If the chiller system lets the coolant get too warm, it fails to pull the heat out of the stator.
Right.
But if the coolant is pumped in too cold, you risk rapid condensation forming inside the electrical housing, which will just short out the motor.
Oh, that sounds like a nightmare.
It is. Worse, extreme temperature differentials cause uneven thermal contraction of the housing metals, which actually physically warps the spindle cartridge.
Okay, here's where it gets really interesting, though, because we all know that metal expands when it gets hot, sure.
Yeah.
But in a multi-ton, heavy-duty cast iron CNC machine, is the thermal growth radiating from just the spindle motor really enough to throw an aerospace part out of a submicron tolerance? I mean, does a little heat actually ruin a part?
If we connect this to the bigger picture, it absolutely does.
Hmm.
Because over long production cycles, a tiny temperature rise turns into rejected precision parts due to a phenomenon known as axial spindle growth.
Axial spindle growth. Okay, what is that?
So if the internal temperature of a motorized spindle rises by even 3 or 4 degrees Celsius over a continuous shift, the physical metal of the spindle shaft elongates.
It actually stretches.
It literally grows downward along the z-axis toward the part being machined.
Okay, so the computer might be commanding the machine to cut a pocket exactly 5 millimeters deep. But because the entire solid steel shaft has literally stretched from the heat, the cutting tool is sitting lower than the machine realizes, cutting like 5.01 millimeters deep.
Exactly. And in industries like medical device manufacturing, where, a titanium bone implant must match a digital model perfectly, a variance of 10 or 20 microns means the part is rejected.
Wow.
You've just wasted the material, the tooling, and all that expensive machine time.
That is wild. And to combat this, the highest-end machines deploy CNC thermal compensation, right?
Right. Which is not just the machine randomly guessing how hot it is.
No.
No, it's a highly complex algorithmic process. The engineers embed thermal sensors directly into the spindle bearings and the machine casting.
Okay.
As the machine runs, the CNC controller constantly monitors those temperatures and maps them against the known thermal expansion coefficient of the spindle shaft.
Ah, so it knows exactly how much it's going to grow.
Yeah, it's a real-time kinematic map.
Yeah.
The computer calculates exactly how many microns the shaft is currently expanding and seamlessly, invisibly shifts the machine's vertical axis upward by that exact microscopic amount to keep the tip of the tool perfectly stationary relative to the part.
Wow. It is continuously, dynamically dodging the laws of physics.
Basically, yeah. Now, Bricks drive spindles manage thermodynamics with significantly less algorithmic gymnastics.
Right, because by physically moving the motor outside of the spindle cartridge, you immediately isolate the largest source of electromagnetic heat completely away from the tool interface.
Exactly. Now, the spindle bearings still generate friction, and that warmth must be managed. I mean, many modern direct drives still utilize cooling jackets around the bearings, but the thermal load is far less aggressive.
It's manageable.
Very manageable. The axial growth is predictable.
Okay, but when you have an environment this extreme, metal spinning at 60,000 RPM, liquid cooling jackets fighting extreme heat, immense radial loads eventually, physics wins, right? Components wear out, and the true cost of these spindles becomes glaringly apparent when they break.
Oh, absolutely. The initial capital investment in the machine tool is just the beginning.
Right.
The hidden costs of maintenance, repair complexity, and factory downtime will often totally dictate the life cycle profitability of the equipment.
Okay, so let's look at the repair process for a motorized spindle. The sources describe it as an incredibly fragile, specialized operation. Because it is a unified zero-transmission system, you can't just, unbolt the broken part on the shop floor.
No, not at all. A fault in a motorized spindle could be a burned-out motor winding. It could be a degraded precision encoder, a microscopic leak in the liquid cooling jacket, or just failing bearings.
Yeah.
Rebuilding it requires an absolutely controlled environment.
Because the manuals explicitly mention that internal bearing replacement requires actual clean rooms.
Yes, because introducing a single particle of airborne dust into ultra-high-speed angular contact bearings will cause them to score and fail prematurely.
It's just a piece of dust.
Literally. Furthermore, repairing these units involves setting exact bearing preload.
Okay, and preload isn't just tightening a nut, right? It's a calculated internal force.
Right. The technicians have to apply a very specific, calculated axial force to squeeze the bearings together, ensuring the steel balls are in constant, rigid contact with the inner and outer races.
So it removes literally all microscopic wiggle room.
Exactly. But if the preload is too loose, the tool vibrates. If it's too tight, the friction generates so much heat, the bearings literally melt together.
Oh, man. And once it's reassembled, it has to undergo high-speed dynamic balancing, right?
Always. Because if the newly rebuilt spindle is even a fraction of a gram heavier on one side, and you spin it up to 40,000 RPM, the centrifugal force will cause it to violently vibrate itself to pieces.
Wow. So because of this extreme complexity, a factory really cannot repair a motorized spindle in-house.
No, the entire unit must be crated and shipped to a specialized repair center, and this leaves the machine down for days, or usually weeks.
Which is a disaster for production.
Huge disaster. To prevent bleeding money from halted production, a facility is often forced to purchase a secondary, fully built spare spindle cartridge just to keep sitting on a shelf.
Just in case. That is a massive upfront capital expense just for an insurance policy.
Yeah, it hurts. Direct drive spindles, by contrast, are fundamentally modular mechanical systems.
Right. They are essentially a stack of separate components. You have the external motor, the coupling, and the mechanical spindle cartridge housing the bearings.
Exactly, which drastically alters the maintenance economics.
Right.
If the external motor burns out, a technician unbolts it, drops a new motor on top, and the machine is running the same day.
So you don't have to rebuild the ultra-precise spindle cartridge just to fix a burnt copper winding.
Exactly. And if the coupling wears out, you just swap the coupling. The potential for on-site, garage-style repair on the factory floor is vastly higher.
So what does this all mean? To me, it sounds like the direct drive is the practical, reliable workhorse you can fix in your garage, while the motorized spindle is the hyper-tuned F1 car that needs to be sent back to the factory lab when it coughs.
That's a great summary. And this raises an important question, right? Because it forces manufacturing engineers to make a tough calculation regarding life cycle cost versus production value.
Right.
Motorized spindles demand a small fortune to purchase, they require complex liquid chillers to run, and they are punishingly expensive to repair.
But if your facility is contracted to manufacture highly complex, high-margin aerospace components or, delicate micro-machine medical devices, the blistering acceleration, agility, and flawless surface finish provided by that motorized spindle will easily justify the maintenance nightmare.
Absolutely. The machine pays for itself in volume and extreme quality.
Right. But conversely, if your business model relies on heavily roughing out moderate tolerance steel brackets day in and day out, buying a motorized spindle is an economic disaster.
You will literally shatter the expensive machine.
Wow. So you match the structural reality of the direct drive spindle to the economic reality of heavy, predictable material removal. Okay, to pull all these threads together for you listening, motorized spindles are the undisputed kings of extreme speed and fine finishing. By integrating the motor directly into the shaft, they eliminate transmission vibration and achieve just breathtaking agility. But they demand rigorous thermal management and highly specialized clean room maintenance.
Right.
Whereas direct drive spindles separate the motor to offer a highly practical modular balance. They provide the low-speed torque and structural rigidity needed to push through massive blocks of metal, combined with manageable heat and cheaper modular serviceability.
And, when you look at all these engineering hurdles, the liquid cooling systems, the perfect dynamic balancing, the real-time kinematic thermal compensation algorithms, it reveals just how much effort we expend to keep friction and heat from destroying the machine.
It really does.
It raises a fascinating question about the future of manufacturing.
Oh, what's that?
Well, as we relentlessly demand smaller and smaller micro-features in our technology, pushing tolerances from microns into actual nanometers, we are approaching the absolute physical limits of what rotating metal can withstand.
Wow, yeah.
Will the sheer realities of thermal expansion and physical friction eventually force us to abandon rotating cutting tools altogether in favor of non-contact machining like lasers or electrochemical erosion?
That is an incredible thought to end on. As tolerances get smaller, the mechanical friction of spinning a tool might become the ultimate barrier we simply cannot engineer our way out of. Thank you for joining us on this deep dive. Keep questioning the physical mechanics of the world around you, and we'll catch you next time.